Yeah, this is super cool. This dude.
I haven't actually met her. I know a lot about him.
This is a lab optimization. What? Yeah, this thing has 7,000 million. This thing has 5,000. Yeah. This gets 20 out of that. This smaller screen, a weaker chip, gets like 10. Is that an Apple device? Yes, not a problem. What if this is Apple too?
Oh yeah, searching with Apple devices. Don't start working too much or they explode.
What? This is basically a screen bolted onto a bat.
Okay, Dylan is online today. Can you hear me?
Yes, I can hear you.
Are you sick? Are you okay?
No, I'm fine. Just ran late to class, so just hopped online.
Okay, no problem.
You could just present virtually.
All right, so I'm going to bring up Juliet's list. So this is Juliet's. Okay.
Can we do this later?
So I give you entire class period if you want it. So please spend your time, no pressure, please.
Oh, I'm starting. Oh, I'm starting now.
Yeah.
Oh boy.
Let me take English. Okay. Today is the last day of the lecture of this semester. So today, this section 03, 1 p.m. class, I'm going to invite you two students working on a special assignment, which is essentially Xfire 5. So this is basically a demo of what you can do on Xfire 5. And also, if you have questions, as you work on your own project, which is due, I don't know, Friday. Today is Wednesday. So if you have any question, please ask him or ask Stephen.
Please don't ask me. Please don't.
It's all yours now.
All right, so this project will just serve as a little tutorial and I guess analysis on the different types of things you can do in Xfire 5. So I guess to start with the project, this will be applied to when you guys start doing your project. You're going to want to start doing a Xfoil airfoil analysis. So I've gone ahead and imported four different airfoils here, and the 4 different airfoils I chose, I picked 2 conventional airfoils and 2 non-conventional airfoils. I kind of wanted to, when I was performing my results, I wanted to get different data points for each different type of airfoil. So I have 2 conventional, 2 non-conventional, and 2 symmetrical airfoils and 2 cambered airfoils. And essentially, I essentially wanted to go with a wide range of airfoil types while keeping the number of foils to a minimum because I didn't want to have a long list of like 20 different airfoils. So the first foil I have here, it's a NACA 0018. It is a symmetric and it is a conventional airfoil. And what I did is I plotted different aerodynamic coefficients as a function of Reynolds number. So you can see these different analyses here. They are in Reynolds number increments from 200,000 to 1 million in increments of 100,000. And if you click on the analysis, what you can do is you can view each of these little data points, each of which correspond to a different angle of attack. So I ran the analysis from -5 to 10 degrees angle of attack. And essentially what you can do is in this little display down here, you can select all the different parameters you want to view for your airfoil. So you can view displacement thickness. So you can turn on and off the visual for the boundary layer. You can also, come on. I can use the mouse. I'm using the trackpad, I'm done.
Okay.
And then, so you can turn on and off your visualization of your boundary layer. You can see your pressure distribution on your airfoil surface and the location of the center of pressure right here. And you can even turn on a little animation, and it will cycle through all of the different angles of attack that you have listed for your airfoil analysis. And it'll show you how your pressure distribution changes, the location of your center of pressure. It'll show you how the boundary layer is affected as the airfoil changes from a different angle of attack. And
You see that dip? That's the transition point of the boundary layer.
yes,
Oh, yeah, so I messed with that, but like, how do you change the colors?
The
Like,
colors
automatically
here?
without having to like do it like individually?
the colors of the graph, the foil down here, or the plots.
The plots. Because
Plots.
like, I see that you have a different wide range of colors, but when you usually plot it, it's like one single color for each.
Yeah, so the version of XFlyer I made this in is actually a newer version that allows you to change the color easier. But in the version I made it, you would simply right-click here, and then a little menu would come up for style, and then you would just click color, and you can choose between a wide range of colors. Unfortunately, it is not here, but if you did want to change the color, you would click on the little colored bar here, you would right-click, there would be a little menu that pops up that says style. You can change the color, the marker size, the width, the design pattern, things like that. But that's essentially how you do it. It's not on this one, unfortunately, no. This is, I did it on version 6.53, this is version 6.50, so.
So it does it for you?
In version 6.50, it does it for you, and I'm not quite sure how to change it.
It's obvious.
But in 653, it's a lot easier. Yeah, yes, Peter.
In XFlyer, so you know how your NACA code defines the shape of your airfoil based on like certain geometry that's given in each number?
Yes.
Can XFlyer like take that number and just generate a wing from it, or do you, or did you just give it the name of NACA 0018 and you had to input like your camber thickness and your
No.
a bunch of your dimensions?
No, you can literally, so all NACA 4-digit airfoils are automatically kind of associated in a database.
Oh, sweet.
So what you do is you go to foil, or no, you go to design, you go to NACA foils, and you can see a 4 or 5 digit,
5 or 4 digits.
4 or 5 digit NACA code. You can just put it in right there, and it'll generate any of the 4 or 5 digit airfoils.
Super cool.
What I had to do to get my non-conventional airfoils, my NACA 6 series, is you can go on a website Dr. H provided called airfoiltools.com, and you can essentially look for an airfoil that you want. You can download the data points as a as a file, and then you can go in here. Where is it? There's a certain command you can do to essentially take a data file you can download online and input it into XFoil.
Sweet. Thank you.
I wish I could.
No.
Yeah, Stephen, you had a question?
You just go to file and click open, you can just select.
All right, file open, and then I have, so these are my 2 non-conventional foils. You can just, it's stored as a DAT file, so you just go with file, thank you, Stephen, file, open, and you find your file path. You can download the airfoil data online as a DAT file, and then you click on it, and it'll generate the airfoil plot right here.
Got it. Thank you.
Yes, Robert.
Cross the trailing edge? Did you cross the trailing edge?
Yes, I did, and you do that by going to,
Yeah, that's what my question.
oh, yeah,
How do you do
so.
that?
I know Dr. H mentioned this in class,
Yeah.
but in order to enforce the CUDA condition and get valid results, you want to make sure you have a well-defined trailing edge so that the airfoil is fully closed, because with all of these airfoils, actually, for some reason, the trailing edge has a little spot that's open.
Mhm.
And what you do to essentially enforce the CUDA condition and make sure that your trailing edge is well-defined is you would go to foil, and then you would go to current foil, and then you go to, where is it? Actually, what you can do, you have to repanel the foil globally, and here it is, refine globally, and then you pick the number of panels. So it starts off as 99, and there will usually be a little gap here. I changed it to 100, and you can pick the coordinates of where you want to place the final point, and you just place it along the chord length or wherever your trailing edge has to be defined, so that you can fully close your airfoil, and it essentially will make sure that your results aren't, invalidated by the fact that your airfoil won't be completely closed.
What do you mean by click? Like you just click on that red dot right there? Or?
What are you talking about?
Like what do you mean by, what do you click on to like close it?
To close the
trailing edge.
Oh, so essentially, and it'd help if I had a non-closed airfoil here, but usually when you input an airfoil into XFlyer 5, the trailing edge Some of them, it autofills it, but for a lot of them, you will find a little point where the trailing edge won't be completely closed. So if you have like a diagram of your airfoil, there will be, if you zoom in really closely, there will not be a data point connecting the upper and lower surfaces at the trailing edge of your airfoil. There will just be a little gap, and the airfoil will essentially be open, and the results, the data will get you will effectively be useless. So in order to fully close the airfoil, well, you have to fully close your airfoil to get proper results. Is that, I think, the best way to put it.
And you have to have a credit condition to have a real result.
Yeah, because
Yeah, that's right.
if you don't, your results won't be realistic and they'll be meaningless. Yeah, so any questions after the project, let me know, and I can probably try to explain it better when I'm not up here. But yeah, if you want to define your closing edge or your trailing edge and you want to close your airfoil, you go and you.
You don't have to show the details.
Oh, okay.
Don't worry.
Okay, I'm.
It's part of the project, you know, still.
Okay. Well, anyways, one of the main things I wanted to show was just the different animations and the change in the different quantities like pressure distribution, center pressure location, boundary layer position, and your lift force plot as angle of attack changes. So, and that's for the airfoil analysis. Obviously, you can. This particular example here is at it's the NACA 0018 airfoil, and it's tested at a Reynolds number of 200,000. But what you can do is you can, let's say I want to do it for a different airfoil, say this one here. You can pick your airfoil, pick the Reynolds number you tested it at, and then just run the analysis, and you can see it'll generate all of your different data points. And
CP is a lot different because this is enhanced regular flow.
yeah, well, the main difference between this one and the previous one is that these are both symmetric, but the first one was a conventional airfoil, and I believe for the NACA 008, the maximum thickness was at 26-ish% chord, but this one, it's, I believe, actually it says down here, the maximum thickness at this particular angle of attack, I should specify. The max thickness position is at 34% chord, so you can see that it is definitely not a conventional airfoil. And then another thing that I wanted to do, once you're done with your airfoil analysis, if you want to start building wings and doing rather than quasi three-dimensional analysis, go into proper 3D analysis, you go to module and you go to wing and plane design. And then this is where you can start building wings and applying your airfoil to perform some 3D testing. So initially what you'd have to do, you would have to go to plane, and you would have to define a new plane, and then you would get this menu that you can fix all your parameters. You can define your main wing, your second wing if you want to do a biplane. You can do your elevator and your fin, but for the sake of this, I've only gone with a main wing. And if you can pick your scaling and your parameters after you create the wing, going into, oh wait, no, that's the analysis, by just right-clicking, going into edit, and then you can change it at any time in case you want to, I don't know, change your parameters if your wing has been, I guess, constructed incorrectly. And I guess the main thing that you would want to do when you're defining your wing is that if you perform the airfoil analysis first, all of the different airfoils you've incorporated will appear in this list, so that once you've performed the analysis with your airfoil, you can put it into this drop-down menu here. So that's the quickest way to take airfoil data and make a wing with that airfoil and then run some analysis, which I'm going to show you. Let's just discard those changes for now.
That's Zoe.
Yes.
For the maximum thickness, is it supposed to be 25%?
For a
It's
conventional
conventional
airfoil, yes. It's supposed to be around 25% chord length, but the airfoil I showed was non-conventional, which means the maximum thickness is not at quarter chord. It's moved further behind the chord length.
Okay.
That one, it was at 34% chord.
Okay, yeah.
So for
5 digits comes with quarter chord as the maximum thickness. That's conventional design.
and those were both 4-digit series airfoils anyways.
Yeah.
So what yes, Michael?
I had a separate question, but it's about flying. I don't know if you're going to get to that later or if I should ask it now.
You can ask it now.
Okay, so when I've been plotting recently, I've been getting a lot of unconverted data points. What did you find as a way to fix that?
Okay, so usually when you get non-converged data points, it means that either your interval, are you specifying with angle of attack or lift coefficient? I'm guessing angle of attack.
Angle of attack.
Okay, so that usually means that the distance between your data points or your sequence is much larger. Most of the time, if you decrease the distance between your data points,
For that.
it will usually fix that issue. If not, you'll have to run a type 4 polar analysis to reconvene the points for certain angle of attack intervals where your error is appearing.
Got it.
Any other questions? Okay, so I guess the main thing I wanted to show you that I think is really cool is when you have your wing constructed and you want to perform your analysis, you would essentially right-click and then analysis, and then define analysis. And then these are the different characteristics that you can, set your analysis to. You can fix the speed, you can fix the lift, you can fix the angle of attack. For this type of analysis, I wanted to fix the speed. I set it to a constant speed of 120 feet per second. And then I plotted it from a range of 0 to 10 degrees angle of attack in increments of half a degree. You did that by clicking on the analysis you defined and then setting in.
Just to pause for a moment. Whenever you choose that condition, make sure you compute the Reynolds number. So if that Reynolds number doesn't match up with the database you built, it's not going to interpret the data at all. So make sure you need to be consistent between your 2D and 3D design. Reynolds number need to match up in the range that you built your database. Okay.
Yeah, and for all of these, I use the same Reynolds number database, starting from 200,000 to 1,000,000 in increments of 100,000.
Yeah, in other words, raw speed, if you set the speed low, Reynolds number gets brought down if you set the high speed. And also, if you change the code range from root to tip, it is going to change Reynolds number too. So make sure you keep track of the Reynolds number of each cross-section of your design wing. Otherwise, sometimes data goes outside of your database you built. That's not going to compute anything. It's usually come up as an interpolation error.
Okay, and then once I've sequenced the angles of attack, in this case from 0 to 10 in increments of quarter degree, which you specify over here, then what you can do is you can click on your initial data point, and then you can display all the different parameters that you want. So let's say I wanted to plot, I don't know, lift value, your induced drag, and your downwash, and I wanted to get an animation of how it is affected over time. You can see that XFlyer is cycling through all of the different angles of attack, and you can see how the different properties are affected as the wing increases in angle of attack.
Can you click on viscous drag too?
Oh, yes, I can.
Because viscous drag is essentially profile drag.
Yeah, they're the same.
Drag is what's set when you choose your cross section. However, the induced drag, as you pitch up and pitch down, you increase the lift. Of course, it is going to skyrocket. That's called induced drag.
Yeah, Robert.
If you made it a flat plane instead of like it bending, does that make sense? You see how the front is bent when you're facing from this side? Like if you made it a flat surface type of plane.
Oh, you mean a tapered wing?
Yeah, it's tapered wing right now.
Yeah.
But if you make it just like a rectangular.
Yeah, I can
Constant code.
Does
I
it
can definitely. The wing I essentially wanted to test in here. I just looked at the specifications for a P-51 Mustang wing and put it in there because I thought that'd be cool. But if I wanted to do that, I could go to my NACA 008. I can go to Edit. I could go to Redefine, and I could change the offset to 0, and I could change the chord length to match the. I can set the root and tip chord to equal. And now I have a fully symmetrical wing.
And it changes the drag induce and all that?
It will if we reperform the analysis. So we're going to have to, when you redefine your wing, it's going to get rid of all your results. So what you're going to have to do is you're going to have to click on your analysis again, and you're going to have to resequence it on your given interval and hit analyze. And then it's going to give you completely different results based on the new wing versus the old wing. And then when you resimulate, you will get different values.
And you can actually simulate wing topologies.
Yes, you can.
Yeah. It's kind of
interesting. What you can do instead is you can go to stream, and it will show you the way the free stream is, or I guess the way the streamlines around the airfoil are affected as it travels, in this case at a given velocity of 120 feet per second. So if you want to see, say, the way the flow stream is affected of the wingtip vortices, you would go down in your display analysis and you would click stream, And then when you hit animate, and let's get a better view of that, you can see that as the angle of attack changes, you can see the wingtip vortices begin to grow. And because I changed it to a rectangular wing, the wingtip vortices won't be very large, but you can see on the edges how the wingtip vortices are beginning to generate. And if I wanted to, I guess, give you a greater example of, I believe it's this one, of say let's go ahead, analyze that, and then let's display the stream and animate that. And because this particular airfoil is cambered and non-conventional, the wingtip vortices will be much larger. So this is just a greater example of how to see wingtip vortices in Xflyer. Yes, Robert.
Since the flow is going behind the airfoil, is the flow negative? Does that make sense?
No, what you're seeing is this is the wingtip vortices formulation. So
Okay, so
you're
it's
seeing
not-
streamlines.
Okay,
That's
so
what
it's
it-
actually going.
So this is front of view, right?
Okay.
Yeah, this is a frontal view. I
Yeah,
just
you
wanted
can turn
to,
around. Go ahead, turn around. Rotate, yeah.
yeah, I just wanted to, that was a head-on view. I just wanted to show you how the wingtip vortices are forming because it's the easiest view to show how the streamlines are being altered as the wingtip vortices begin forming. Yes, question?
Yeah, so, now there's like a starting vortex for when it just starts in the speed. Is it starting
Starting
in?
vortex is not this. This is the wingtip vortices on steady state, right?
What?
So in other words, as you change your angle of attack, it is going to change it. It's a different value for it.
Yeah, I was,
Because you're animating angle of attack.
yeah, I was just asking whether or not when you start the animation, does it start at 0 and then pick up the velocity? Is that why you?
No, velocity is always constant.
Okay.
For this type of analysis, I set the velocity constant at 120, and I changed the angle of attack. But what you can do is you can run an analysis with a varying velocity. It's just for this particular analysis, I wanted to keep velocity constant and vary angle of attack, so you can see how the vortices were changing as your
So
angle of
that's
attack.
why I did it.
Yeah, but to answer your question, the analysis will always start at your upper bound, or your lower bound. So I can click this data point and see how the streamlines are being affected by the wing. And yeah, you can also do pressure coefficient plots as well, which I think is pretty cool. If you go to animate that, you can see how the pressure coefficient is changing as the angle of attack for the wing changes as well. Yeah, so there's really a lot more I can show you, but you can also do pitching moment, you can do viscous drag, lift, induced drag.
And also F over S is a surface force distribution, which actually you can pass out this data into the structures people so that they can design, structures. This is a wing loading. So they need to design strong enough wing to sustain that wing loading. Okay.
Is it only showing the maximum?
No, this is the force distribution over the surface. F over S is for QACP. So this is wing loading. How much force distribution over the surface is happening over this wing? So structures people need to know this kind of thing.
It's not maximum or minimum. Each value is given a color code, and the magnitude of that color is given in the bar here. So it's not just plotting maximum and minimum. It's plotting all values across this entire wing.
It's a distribution of the force over the surface.
Yeah, so it's not just a singular maximum minimum value. It's across the entire wing.
Zoe?
Yes.
Yeah, it's okay. So you were showing the wingtip vortices earlier.
Yes.
Can Xflyer, and it's okay if you don't know the answer to this question because this is a bit out there. Can Xflyer simulate wingtip devices as well?
Yes, you can.
I was gonna ask about.
Yeah, like winglets and fences.
Yes.
Oh, shoot,
In order to simulate winglets, you have to redefine your wing and include winglets, and then when you click on the stream, it will show the effects. But
Oh,
because
cool.
for this particular wing I designed, I didn't include any winglets.
Right.
But if I go
Can
to
you go
the
back to the design panel?
for the wing design or for airfoil analysis.
Wing design panel.
No.
Yeah, that actually.
You would
shows the
able
wing tip, right?
essentially if you wanted to create wing devices, you would have to redefine your wing, and then you would. If you see here, you can add different sections.
Oh, and then you would add dihedral and then make it.
Yeah, so if you wanted
yeah.
to add a winglet, you would add some taper, you'd add some dihedral, and then you could
Actually, can you go back?
go back.
To the panel. Yes. Yeah, yeah. So you can actually do a biplane also if you want to, and you can actually add a fuselage. Those are the control surfaces, so this belongs to the fragment class, not aerodynamics.
Yeah, when
So
you,
those are needed to come up with the stability analysis of them.
if you really wanted to get more accurate results, you would include a fuselage, but for the purpose of this class, it's kind of outside of our realm, our material.
If you take fragment professor, if they are interested, they will probably take it further.
Yeah, and ideally, if you wanted to, because you can, I just showed the creation of a simple wing, but you can create entire planes in here if you define an elevator, a fin, and the way you define those is very similar to the way you define an actual wing. You can import an airfoil and give it specific dimensions, root chord, tip chord, taper, aspect ratio, and then completely design a plane from scratch rather than just doing a wing here. But I just did a wing for simplicity's sake, just kind of to show you how X-Flyer 5 works. Yeah, Robert, question?
Yeah, why does it say X and Z? Is that the positioning of where you would put?
Yeah, so I was initially messing around with adding an elevator in the fin, but I decided to scrap it. But if you see here, the X and Z, those are the coordinates of the individual component. So I have my wing centered around the origin. But let's say if I wanted to include my elevator, the X and Z component, this would change where the elevator is positioned. So let's say I want to decrease this to 3. It would make the elevator closer to the wing. It's essentially defining where that component of the plane exists in the coordinate system.
Oh, is it using the same airfoil too?
No, it's not.
Oh, so you created a
In this,
elevator.
yeah, well, I did, but I decided to scrap it. But in this case, it is using the same airfoil. But if I wanted to change it, say I could go in here and I could pick any of the airfoils I've already performed an analysis on in Xfoil. So it doesn't necessarily have to be the same airfoil from your elevator and your wing. You can, as long as you have it defined and analyzed in Xfoil, it'll appear in this list, and you can apply it to a wing or an elevator in X-Flyer 5. So I initially did create this, but I decided to discard it. So that's why you can see why the coordinates are where they are. It just allows you to change where that component is placed with respect to the origin. Yeah.
We got another question here.
Yes, questions?
Yeah, so for the elevator, for example, where is the origin located that you're using your coordinates to position? Is it at the tip of the was it root chord?
In my case, let me go back to that. So when I was making this wing, the origin for your coordinate system is always defined as the leading edge of the wing at the center. So the way you build wings in X-Flyer 5 is you're essentially building half a wing and then making it symmetric across an axis. So when you specify, you don't specify a wing span, you specify a distance that is essentially half your wingspan. And then actually I can show you, because if you see when I define my wing, my this y value here is the y displacement from your axis here. So this distance here would be 3.7 feet, but my wingspan is 7.4 feet.
Okay.
So it's effectively doubled because it's mirrored across, and you can pick between right and left side here. So let's say if I was a madman and decided to make the left side of my wing, much smaller. I don't know how you want to do that, but you can effectively choose between your right and left sides and edit them as you see fit. But
I think Stephen may not have enough time. So let's just limit maybe 2 more questions.
Yeah.
What units do you use for these?
When in this, I used feet because that was the default. But if you want to change them, you would, let's just discard that. You would go to, let's discard that.
Like millimeters versus meters or whatever.
Yeah, you'd go to options and you would go to preferences, and then you can go to units and pick all the different units you want for any different quantity. I defaulted to feet because we're in America. Deal with it.
Okay, maybe one more question. Go ahead.
Yes, question.
So let's say you're trying to build like a faster airplane wing. So is it possible to rotate the wings inwards, like toward where the fuselage will be?
You mean adding dihedral or anhedral or sweep? Yeah, what you would do is you'd go to edit, and then you can go to define your wing. And if you see here, you can add dihedral. If you want to add dihedral, you'd make it positive. If you want to add anhedral, you'd make it negative.
And then you can change offset.
Yeah, and if you want to make a swept wing, so I have my offset set to 0, which this value effectively it changes the distance between the leading edge of your root chord and the leading edge of your tip chord. So say I wanted to make a swept wing, let's just make a very small sweep. You can see by when I enter 0.125, it will shift the, and this is on the second airfoil, which is your wing tip. It effectively makes the leading edge of the tip airfoil this distance offset from the leading edge of your root airfoil. So the distance between these 2 points along your axis is equal to this distance. So let's say I wanted to really sweep my wing. Let's just, yeah, you can get a that is very unsymmetric, but that is effectively how you create a swept wing, is that you create an offset value from the leading edges of your root and tip airfoils. Yes.
Okay, sorry, Steve, please come up. We are running out of time. Sorry about that.
I have not done a very particular job of covering this, but if you want to know more, just shoot me a text. Well, let me know essentially, because this software is capable of a lot more than what I've shown you. So.
They find out. Don't worry about it.
But if you need help finding out for whatever reason, just let me know, because I have played around with this a little bit. So let's not save that, because those changes were a mistake.
Okay, thank you very much. And next is Steven.
Yep.
This is
Project.
Yes, dude, let's do it 8 a.m. this morning.
Yes, Steven.
It's a fine way.
Yeah.
I like this one.
He's going to show you how an X-Fire project should be done.
So yeah, that's a lot of data.
I
Yeah.
should have shown you guys my draft.
So I'm focusing more on kind of like a flight mechanic standpoint. So my goal is to design like a glider wing, so high aspect ratio. So I did some research. I found general ranges for like aspect ratios for like gliders, and then found general ranges of like the wingspan. And then, so I came up with the aspect ratio of 30 I chose, and then like a wingspan of 12. And then I was able to find the platform area, just using your simple aspect ratio equation. And then you can get your mean aerodynamic chord. And so from there, I then found some ranges for flight velocities. So I wanted to include like the velocity flying in like a thermal, because that is important for gliders. And then like the cruise velocity. So I was able to use that with like my mean aerodynamic chord. I found using like the aspect ratio and span, and I was able to get my Reynolds numbers. And then I just started choosing a whole bunch of airfoils. So I first started off with like 6 or 7 airfoils from Dr. H's airfoil database. There's all NACA airfoils. And then I chose this Selig airfoil, which is a high camber airfoil, which Eagle-Nautics is using. I was mostly just curious to see how it would perform in this sort of aspect. And then I chose some glider airfoils like the Epler AE301, this Hoagie airfoil, and then this one. So yeah, so along with, so here are 2 symmetric airfoils, and then start getting into some camber. And so I'm going to show you some CP plots for different airfoils. So let's take this Epler one, and Okay, so as you can see, here is like, let's just choose 5 degrees angle of attack. You can see this CP distribution. And then if we compare it to a higher cambered airfoil, you can see like the difference. Sorry, none of my data got saved over for some reason for these individual Reynolds number analysis. Sorry. So you can see the CP plot is a lot bigger, and that's just the difference between a high cambered airfoil and a low cambered airfoil. Moving on, I then use some of these, polar plots like CL versus CD and CL versus alpha and CD versus alpha, along with the other ones. And these are just different. These are at different Reynolds numbers. So we can focus on a few. So you can hide all polars, and then you can go through and you can say I want to look at this airfoil, so the AE301, which is one of the sailplane airfoils, and then you can choose. I want to also show this one, the NACA 4412, and then NACA 4415, and then the Selig one. So you can see here, we can actually expand by pressing 1. You can get your CL versus CD graph. You can see at different like CL values, you can see like the corresponding drag. So this is the Selig airfoil, the high cambered one. It has a lot of lift coefficient, but then the drag is a little bit more. So there are some trade-offs you have to consider. So primarily,
sorry, could you please? Okay, with the lift coefficient, it's plotted negative to positive. Don't we usually plot the other way around? Like
this is actually 90. You have to turn 90 degrees
Yeah.
to understand. This
So
is
right.
In like the notes, it was kind of flipped.
Right.
So where your CL was your x-axis, and then your CD was your y-axis. So it's a little flipped. So here we like for like a glider, you wanna value like trying to minimize your drag and stuff. So if we then look at here's your CL alpha. So you can see how your high cambered airfoil, it has your alpha at L equal to 0, like pretty shifted like back. And then you can see that it kind of stalls out a little sooner, maybe around like 12, 13, 14 degrees than like your NACA 44, 12 and 44, 15. And then the AE301 actually kind of stalls out even sooner, so it's not as good performing. Yes.
For the white line, the NACA one that you mentioned, is it upside down? That's why it looks like that.
This white one on the bottom, or
Yeah.
this kind of beigeish one?
No, the last one.
So this is the AE301, and
Does it look or something?
no, it's a
No, Emperor is very slightly cambered thin airfoil.
yeah.
So that's why CL max is lower. However, at the same time, it comes with lower, right?
Yeah, so I'll show that real quick.
Yeah.
Go to the third graph. This is CD versus alpha, and you can see that. Like, so this pink one and the tan and the turquoise one, that's your 4412 and 4415, and those ones have a higher alpha. It has like the same CD value. So that's why I decided to choose those two airfoils moving on. However, I brought all like 4 of these airfoils into the 3D plane analysis because they're the best performing ones out of the bunch. So yeah, and if there are any questions at this point, feel free to ask.
Question. Yeah. So you said they have the same CD or approximately.
So if you go across at CD equal to 0.1, you can see that at the alpha value, it's a lot, less than these ones. So you can kind of see that like it has less drag at higher angles of attack.
Okay.
So you're looking for the optimal airfoil for a sailplane. You're looking for the best performance. How did you measure performance? And how did you decide which is the best performance?
So 2D wise, I was mostly just looking at drag and lift coefficient, mostly because you can't really look at some like flight mechanic type of like equations and values. You need your 3D stuff. So like in the 3D wings, I was able to get my 3D CL and CD values and induced drag, and from that I was able to calculate like the sink speed. And then like basically the time it takes for it to get to the ground that it's gliding. So yeah, I was mostly just looking at your just like CD and CL values, your 2D airfoil values. So yeah.
Yeah, you have to take flight mechanics to find out, but this is the starting point. This is the drag formula, and then you can determine like the gliding range, endurance, and other things based on this data. So if you do a good job in this aerodynamic analysis, I guess this is going to determine your performance.
Yeah, so the whole goal at this stage was to narrow down these 10, 12 airfoils down to like 3 or 4, just so you don't have to make as many like 3D wings and do as many analyses in the future. So I figured I could use the 2D data to kind of help narrow that down. If that makes sense to you guys.
Yeah, that makes sense.
Okay.
Yeah, here's actually quite important thing. This is 2D analysis, right?
Mhm.
When you design a wing and also entire airplane, you have to again plot forward. That's going to determine your airplane's performance. This is only 2D, so you're going to compare 2D data to choose which one is the best bet for your airplane. It depends on the type of your airplane.
Yeah. So like for the Selig airfoil, it has a high initial lift coefficient at like 0 angles, 0 AOA, as we can see. The high cambered one, sorry, this graph. So it at 0 angle of attack, it has about 1.2 or so CL compared to about 0.5 and 0.35. So it kind of depends upon your application. If you need to take off really quick, or you have a high takeoff weight, then you might want to consider like a high cambered airfoil.
Well, you don't have to pitch up to fly, but it comes with huge drag always when you're flying. That's what the high cambered airfoil is. Yeah.
So I'm gonna show the difference. So if you so you can see the displacement thickness. So sorry. So this is at just 0 angle of attack. And when you get to higher angles of attack for like a high cambered airfoil, your flow starts to kind of separate a little bit, as you can see as we move on. So there's high flow separation. And then if you take, for example, a less cambered airfoil, like your sailplane airfoil, at higher angles of attack, it doesn't quite separate as much. So yeah, so I guess we'll move on to some 3D analysis, in which I will cover winglets. So yeah. So I first started off by just like making our first sheet bar wing, it's like a square wing, because I wanted to keep my aspect ratio to something I could easily control. Because when you add taper, you're changing the platform area, and as a result, you're changing your aspect ratio if you leave it as the same like span. So I just kept it as a square wing because I wanted to look at, I wanted to simplify my process. So here is the sailplane airfoil. So you can see like the side profile, it's very slim, and I've just made the wing in this case. And then here is the 4415 airfoil. It's a little thicker. You can see it's cambered a little bit more. And then here is the 4412 airfoil, and then here is the Cellite 1223 airfoil. And these are the airfoils that chose to bring into the 3D analysis. So we can show some polar plots. So the dashed lines, like in the CL versus CD, are the viscous analysis, and you can see that they're a little, they don't perform as well as the inviscid analysis, because all four of the inviscid analysis are very, very similar, but then the viscous analysis, they do change a little bit. And you can also tell, by looking at your CL versus alpha, the same trend kind of happens with your 2D airfoils. So like the green line is the high cambered Cellite airfoil, and then this bottom curve is your sailplane airfoil, and that was congruent with your 2D analysis. So that kind of further backs up some of the analysis. So
this is the wing CL, right?
Yeah, CL versus alpha. So so you can see the pitching moments. They are negative, which is good as a soaring moment. Yeah, so I guess we'll move into some of the wing iterations I did. So I took the 4412 wing, and I decided to add winglets to it. And I added a whole bunch of winglets and got different induced drag results. And I think they're actually pretty interesting. So I first started off by just adding just square winglets. I kind of like capped off the wings, and they go up. And I think that is this one. Okay, so you can see it's just very basic, and it did actually lower the induced drag in here. Yeah, just a little bit. Yeah. So then I was like, okay, so what if I swept the square, the vertical winglets backwards? And I ended up I did choose a symmetric airfoil for those winglets, because I didn't know what a cambered airfoil would do as much. So I decided I just put a NACA 999 in for the winglets to make it symmetric. And then, so we then sweep the squares backwards a little bit, and that was the next iteration. And then I decided to instead of having a square, I just tapered it a little bit. And that is this iteration. So it looks a little bit more like a winglet that you traditionally see on your aircraft. And then I started adding some dihedral to it. So you can see at 80 degrees, you can see kind of the dihedral added at 80 degrees, and then to 75 degrees, and then to 70 degrees, and then to 65, and then to 60. And then I decided to kind of have multiple airfoil sections a part of the winglet. So these two.
Oh, so raking it almost.
Yeah, trying to kind of smooth out the curve in a way. So I was kind of just preliminary, trying to figure out if this is a better design than just a straight winglet. So I then I recorded the CD, the induced drag values. Let me pull them up real quick. So here are the induced drag values at 10 degrees angle of attack. And you can see Some of them are really bad, but I'll go on and explain a little later why it's so bad. I was trying to mess around with adding both a kind of vertical and down. So you can see with no winglets, you have an induced drag about 0.025, and then if you just add a vertical square winglet, you drop it by about 0.005, which is kind of significant for drag-wise. And then you can see if you start adding some like dihedral, you kind of converge on this value, and that was the lowest in the bunch. And the reason why the red ones are so low is because I think XFlyer had a hard time calculating them because I did a biplane design, but it hid the bottom wing inside the top wing. Because it was an effort to create
Like a split scimitar.
it was an effort to create
Yeah, split scimitar.
So some planes have this type of winglet design, and the only way I could figure out how to do it was to add a second wing and then make it identical. And you can kind of see the green kind of poking through. So yeah, I didn't, and that's the value that was negative like 1 million. So it's also negative, which means it's basically accelerating the plane forward, which So then I tried making the bottom biplane wing a little smaller, and I was able to converge to this value, which was on the same magnitude. So, yeah.
Yeah, I think we need to talk to the author about how to solve this. This is something new, it's a new design.
So if there are any further questions, I think we're about out of time.
Say there's this amazing wing that I spent hours building in CATIA, and I transport my design from CATIA into XY5.
Not really, because you need to design from 3D, then using that 2D to design your wing and fuselage and everything. So you're not just
If I told XY5 what airfoils I used in CATIA to design my airplane.
Well, no, I think you have to, your design needs to start from 2D shape to begin with, and then that database needs to go. That's fine.
So there is a way, in OpenVST, you can build a wireframe model of your whole plane and then save it as a certain file type, and you can load it into CATIA, and you can actually do your whole plane.
That's a CFD though.
Go backwards though.
You can do
But
CFD.
that is an option. You can use similar analysis.
Yeah. Okay, so I'm sorry, we are running out of time, but any other final moment question? Thank you very much, Stephen. If you want to show up on 2 o'clock class, I'm going to finish up at Unit D1. And it's going to be videotaped anyway. So
I was really thinking about doing that, but that's 2 hours.
Specify different airfoils along the length for aerodynamic twist?
So you know how I said you can insert a section if you want to incorporate a winglet?
Yeah.
When you insert a section, you get a whole new. Actually, I might be able to show you how to.
No, because like we're running out of time.
Little drop-down menu I showed that allows you to pick an airfoil.
Yeah.
When you add a new section, you'll add a new row, and you'll be able to. There'll be a new drop-down menu, so you can incorporate aerodynamic twist. And then
Can you put geometric twist in there?
Yes, you can.
And can you specify like different?
Twist in degrees. That's your geometric twist.
Okay, and does it have to be the same along the whole length, or can you like,
this is for something.
if you're dividing it up into sections, can you have different amount of geometric twist in different sections?
Yes, you can. Because each section, when you click the insert section, it'll add a whole new range of columns, and you can specify everything for that new section. You can change the airfoil, the geometric twist, dihedral, anhedral, length, taper, aspect ratio, sweep.
Well, in addition to CFD, I know what I'm gonna be playing with this break.